Okay, so what I was planning on doing, I've said this a little bit, is I don't plan on taking the entire 2 hours for this. I don't really want to talk for 2 hours. I would love if some of you all would talk for some of that time, especially if it can stimulate some like interactive discussion. What I'm going to do is sort of give a little bit of an overview of what the TRF is, what it does, how we derive it, and then show some of this script and explain what all the different parts mean. Hopefully this talk won't take too long, but I will start with my slide. So I was fortunate enough yesterday to find a talk that I'd given in the past that sort of details all of this, at least the background of stuff that I want to cover today. So a lot of this, like we might get into some of the slides that don't actually apply here, and so please just bear with me as I skip through things that are important, things that are not important. So in this brief, I think it lasted maybe 15 minutes when I gave it the first time. We'll talk about sort of the basis of the TRF, which is built upon linear regression. I'll go from linear regression, the ordinary least squares approach to it, which is what you know is just standard linear regression. I'll give some context about the TRF and what we're fitting and why we need to not use ordinary least squares regression and sometimes. I'll tell about how we fit the temporal response function and what that means, and talk about how we validate that model. And then give a few examples of like what we can do with the TRF, a few findings that some of the group has found. Some of these things like envelope tracking, I'll cover in the code and some of the model comparison stuff, but some of the things I won't, like for example, the cocktail party decoding and some multi-sensory stuff in here that I won't compare, just to give you a sense of like, one, what you can do with the toolbox and show you how we do that, but also to give you a little something that you can do on your own and figure out yourself, so I'm not giving you all the code. There's a lot that the toolbox can do. So essentially, the MTRF toolbox is just ordinary linear regression with a ridge regularization. And so here, let me actually get a pointer so that you can see. So here's like a pretty standard view of linear regression. You've got your input X, it gets multiplied by some coefficient or some weighting parameter beta here. We add some error term, and then we get the output Y. For the TRF, the X, in the forward direction at least, the X represents your stimulus feature, and the output Y represents your EEG signal. We sort of ignore this error term, and then what we do is we fit this beta coefficient. We can estimate that coefficient using the ordinary least squares estimator just by taking the design matrix of X, transposing and multiplying by itself. This gives us an autocovariance matrix of our stimulus. And then what we do is we take that and we divide that from the XTY, so the transpose of the stimulus against its output response Y. So this is really doing all the business here, and then we divide out the autocovariance of X to get our coefficient. And once we have this coefficient, or set of coefficients, as it were, we can then apply those coefficients to some other or to whatever stimulus parameter and get some estimate of what the EEG activity on that to that stimulus would be. This is sort of the basis of the TRF, fit and predict. So as I said, the Y represents the EEG signal, the X represents the stimulus, and that stimulus can be really anything. Most of the time we'll be talking about the stimulus envelope, but it can be a spectrogram, it can be labeled onsets of phonemes, it can be, as shown here, the labeled duration of phonemes, it can be a semantic predictor that's a stick at the beginning of each word with the stick height representing like how surprising that word is. And then from that, we're gonna derive some beta coefficient. But first, a little bit about X and about what it looks like. So the X is a stimulus representation that we're going to input into the TRF. But because the stuff happens in the brain after it happens in the environment, we need to see what happens for lagged versions of X. So here is the original envelope. And so what we can do in this X design matrix is to shift the envelope upward, sample by sample, so that we can see the response before the stimulus. So here, this would be your standard linear regression. Here, we're pairing the second sample of X to the first sample of Y. So this gives us the response before stimulus. So like the second stimulus is happening before the brain response, which is not physiologically possible, generally speaking, with respect to predictions, maybe, but this side gonna give us a response before the stimulus. Conversely, when we shift the envelope or whatever stimulus feature downward, we're matching up the first element of the stimulus with later elements of the response. So more physiological, what you would expect according to a feed-forward model. So to the right of this one, we're going to get the responses after the stimuli. And so each one of these columns of X is going to represent the stimulus feature at different lags. We can pad the edges with zeros, or we can just cut them out of it. The TRF can do both of those operations. But introducing all of these lags gives us a little problem. So each one of these columns is treated as a separate coefficient, essentially, in the TRF. And when we do the XTX, we do get some of the autocovariance between these, but we do need to like regularize this because of the multicollinearity. And so, oh, I forgot to mention, we do have an intercept term. We usually like z-score all of our stuff so that it's centered at 0, but this will help, any centering issues. So because we introduce a lot of these lags that are essentially perfectly correlated with each other, aside from the lags, we need to account for that. And the way we do that is by transitioning to ridge regression. And the ridge regression solution adds 2 terms here to be added to that covariance matrix. Lambda, which is our regularization parameter, and I, which is an identity matrix. This is why we call it a ridge, because the I is just a 1 across the ridge of the diagonal. The lambda, or regularization parameter, will tell how much we want to emphasize that main diagonal, which includes, time lag 0 with time lag 0. So we're going to emphasize that main diagonal, and that's going to do what's called regularization. It's going to control for overfitting. It's like what tends to happen is that the slopes will vary wildly because there's a lot of noise in the signals, and so this will just sort of control that. You'll see more about this tomorrow in some of the tutorials. So once we fit these things, we get the beta coefficients across time lags, which is actually the temporal response function. I remember when I was a grad student reading some of Ed Lawler's papers about temporal response functions. I had no idea what they were. They were magic. And in fact, they were magic to me for the first couple of months that I was in the lab. And then I realized one day, I don't know why I realized this and why it took me so long to realize, but these are just linear regression coefficients. These are just slopes. So what this point right here means is that this long after the stimulus, the EEG tends to be high when the stimulus goes up. So like when a word onsets, you get a big influx of the envelope, and then probably about 100 milliseconds later, the EEG tends to be high. That's all that means. It's just a slope. But of course, we can't just fit and predict on the same data, because that would be hella overfitting. So what people end up doing for these sorts of experiments, and the data that we're going to use today is like this, is you'll have someone in an EEG cap that's just paying attention to some stimulus. In this case, it's going to be some audiobook, and they're just listening to audiobook chapters. They're asked to answer some comprehension questions, but they're just listening to a book for all they know. The book is divided into segments that are like manageable times, 3 minutes or so per trial, but we get some speech segment that they listen to for each of these trials. We also get their EEG for those trials. And we can use some of those trials to fit a model. So we can take some of the stimulus features and we can take some of the EEG channels and we can input those into what we call TRF train. And we can fit a forward or a backward decoder model. And we can take, somehow went backwards. Then we can take some other trials after we have this fit model, and we can use them to test that model. So we'll take a stimulus feature and pass it through the model and get some EEG prediction. Or if we're going in the backwards direction, we'll take the EEG, pass it through our backwards model, our decoder model, and get some stimulus reconstruction. Of course, we'll take the other signal and correlate to that, right? So this pathway here represents MTRF train. This pathway here represents MTRF predict. We'll go over these functions later. But this process altogether, what we typically do is take a bunch of trials, fit a model, and train on the left out trial, and we'll rotate this left out trial. And this process is MTRF cross-val, which I'll talk about later too. Once we have a fit and optimized model, we can look at that model and look at its weights. And so here are the weights. And if we look across time at a channel at the center of the scalp, we see what looks like a nice ERP, except it's not exactly an ERP, but it's different fit to a continuous stimulus. You can also look at the backwards model decoder weights. This is apparently not a very well regularized decoder weight, but it's there to illustrate a point that we don't typically interpret these backwards weights. You can interpret these forward model weights as actual EEG signal. This is what happens in response to a stimulus. These are a little bit different because what happens is that all of the EEG channels can go together to help predict the stimulus. So you get some sort of antagonistic interaction between the channels. And so like some channels, I'll show you a little bit better that later, but some channels can actually get fitted with weights that are not physiological, but serve to sort of increase the sensitivity of that signal. Well, we can transform those weights into forward-looking weights, and that's cool. Skip that. So we can use the MTRF toolbox to track ongoing speech. So here is an example of something that I won't talk about during the tutorial, but that's something that is part of the toolbox and you can do yourself. The data are out there and the tutorial code is free. In this experiment, we were interested in understanding what are the consequences of coherent audiovisual stimulation. So we had people watching visual speech, listening to audio only speech, and then watching audio-visual speech. And we can fit decoder models on the visual and the audio speech and on the audio-visual speech. And if, again, these are tested and trained on their own data set. And then the TRF has this other function called MTRF multi-cross-val that can fit a decoder based on the visual and the auditory only and test on the audio-visual. So this is getting at a sort of multi-sensory phenomenon that we use where we test the audio-visual responses against audio plus visual unisensory responses. And so what we find with these is that when we're reconstructing the stimulus, the visual model and the audio only model, they do fairly well. But when you combine them, they get better at reconstructing the stimulus. And when you combine them and when you fit them on audio visual stimuli, it gets even better still. So V is fit and evaluated to V, A is fit and evaluated to A. A plus V are fit on A and V and then tested on A and V. So what we're doing here is we're trying to see if there's any unisensory things going on in the audio visual condition. And then AV is fit and tested on audio visual. So we've got an A+B decoder that can't predict audio-visual data as well as an audio-visual decoder, indicating that there's some sort of nonlinear process going on in there that's only captured by the audio-visual decoder. And the improvement of this performance is we take as evidence of audio-visual integration. We will talk about this to some degree later, but we can also look at different features using the MTRF toolbox. So far, we've talked about only the envelope model, but speech can be divided into different features like its spectrogram, which is the envelope that's just resolved over frequencies. We can also label the occurrence of phonemes. We can combine those phonemes into phonetic features. So like certain features are specific to certain phonemes, and that's what this does. And then we can also have a joint model that we use to fit and predict the stimulus. So these are the examples of those TRFs. Here's the envelope TRF that you've seen so far. Here's a spectrogram TRF, and so what you see here is the different colors correspond to the amplitude, and then the different rows correspond to the different frequency bands. The same thing for phonemes and phonetic features with the colors and the rows. But these can be used to predict left out data with the idea that what we're going to try to do is see if the spectrogram and the phonetic feature model can predict different aspects of data. So one way that we can do that is we can fit a spectrogram model. We can fit a feature model, and we can look at their like representation, how well they can represent data. And the idea here is that they should have some shared contribution because they're correlated. And they should have some unique contribution. Kind of just made it up here. And if things go well, this is what the FS model should predict. And that's exactly what we find, or at least what Giovanni found. And he concluded that phonetic features were represented uniquely in brain activity above and beyond the spectrogram. So when you listen to narrative speech, you're getting both the acoustics and you're getting both the linguistic content. I'm gonna skip that. It's more of the same. It's just my stuff that I wanted to plug. One last thing that the MTRF toolbox has been used for quite a bit is attention decoding. This is one of our most cited papers. I think it's about 500 citations at this point. And what people were doing here is they were listening to two stories. One was in the left ear, one was in the right ear. One of the stories was Journey to the Center of the Earth, and the other story was 20,000 Leagues Under the Sea. And on each trial, they were asked to pay attention to one or the other. And what we can do is we can take the attended envelope and the unattended envelope, and we can fit decoders to both of those. So they were getting both of these stories in their heads. We can see how their brain responds to each story at the same time. And the brain does respond to both stories. We are able to reconstruct the attended and the unattended decoder. But what we do then is we correlate these reconstructions with the actual stimulus, and we do the reconstruction of the attended decoder for the attended and unattended story, and the unattended decoder the same way. And we can look at how well the attended was represented, the attended stimulus was represented as compared to the unattended stimulus. And on a single trial level, the attended story is almost always represented more strongly in brain activity. And so this has become the basis of a lot of different like attentional decoding paradigms. And it's, we have like our own conferences like COG here that's just almost entirely attention decoding. Let's skip some of that. There's some other analyses that I won't talk about. You can find the MTRF toolbox here if you haven't already gone to it. I forgot to put it in here, but we do have a new Python version of the MTRF toolbox called MTRF Pi. Ola will be giving a tutorial about that tomorrow. So I'll stop there. That's all for the background. I'll stop in case people have questions. To see some faces. Any questions? You don't need to raise your hand for this. You can just unmute yourself and interrupt me at any point that you want, by the way. Seeing as there are no questions, I'll just I'll move on. So now I'll turn to the code. So this code can be executed all at once, but I'm going to go through section by section and just control enter each section. So if you're following along with me and I'm going too fast, please let me know. I'll slow down. I'll try to be as slow as possible, but it's going to take all of our inputs to make this thing last 2 hours. So the first thing I'm doing is just doing some dependency issues. I'm making sure everything's closed. Giovanni must have written this one. I don't use clear all anymore. You can run this or not run this. I run this because I have my own startup file. I have a bunch of dependencies already in MATLAB. So I use this to get rid of those. You will need to run this to add all of the dependencies. Oh, look at that. I'm not in the right folder. So let me explain the folder. So you should have your data CND in Lawler Natural Speech here. You should have this code in the example scripts file. And that's why it didn't run, because I wasn't in there. So let me do that again. But you need to run this add path dependencies because we do have these, as Giovanni mentioned, we do have these dependencies that we use in the tutorials and all of the CNSP scripts. Then I will execute this section that's just going to go through and set some parameters. So if you want to change, if you can download multiple data sets, you can change this line here to whatever data set you want here. You can also change the reference type or the bandpass filter rate. Actually, these don't run right now. I'm not doing any pre-processing. I'm using already pre-processed data that were in that data set. And the pre-processing script I'm using looks something like this, where actually I just use the same thing. It's just the average reference, filtering from 1 to 8 hertz, downsampling to 64 hertz sampling rate. And then in there, we're doing a removal of bad channels by looking at neighboring channels. All of those functions are available in the CNSP libraries.
Asking for a friend.
Okay.
How do we find the data CND folder? Like, what URL should we have downloaded the data from?
That will be on the cnspworkshop.net/resources. There are, let me go to that website so I can see what's on there. Do you have a browser here now?
Yeah.
So the resources tab here, the natural speech data set is here. It will download a zip file. It's really big. It probably won't be done downloading by the end of the tutorial if you start it now.
Okay, great.
But inside of that will be the data CND file with the CND data. So I've set a couple of parameters and I'll go and talk about some of them a little bit here.
I have a quick question too.
Yeah,
before you
please.
continue on. So the example scripts that I have all have like example 1, 2, 3, 4. It's named differently than what you have pulled up, or perhaps I'm looking in the wrong spot.
Did you get the email with the tutorial instructions?
Yes, and I downloaded those, and I'm in like the CNSP resources, data sets, example scripts.
Yeah. So take the, so you should have this script and this mat file, or a mat file. from that email and just put it in this folder, example
Gotcha.
scripts.
Okay. Thank you.
Sure. So the first two parameters I'll talk about, Tmin and Tmax, these are going to correspond essentially to what you see in an ERP. So if you're looking at an ERP, you've got the time along the x-axis, and this will define the limits of those axes. So what we're going to do is we're going to fit a TRF starting 200 milliseconds before the stimulus came on to see what was going on in the EEG before the stimulus even happened, all the way to about 600 milliseconds after the EEG happened. I like to use negative lags and a lot of lags after what I think is going to be the bulk of the TRF, just to get a sense of, one, the baseline that's going on before the stimulus happens, just to see how much noise there is in the TRF. And then also toward the end to see the TRF return back to baseline. So 200 minus 200 to 600 will give us that duration. We've got two options for lambda here. We got one that has fewer lambdas that will make this go a lot quicker. This was actually a vestige from one of the previous codes that I took that does this on multiple subjects. The code runs pretty well using this set of lambda, but if you're finding that your code is running slowly, you can comment this or uncomment this by pressing Control T on a PC. Comment this one by pressing Control R on a PC. I don't know what the equivalent is in Mac, or you can just manually take out and insert this % sign. But I'm going to roll with this large lambdas because that's what, or large list of lambdas because that's how I ran the tutorial in my practice. And then also the direction of the TRF. So we're going to start off with the forward model. I'm going to now load and prepare the EEG and stimulus features, and I'll go through a little bit about what's going on here while it loads. It shouldn't take, actually, it's already loaded. So there's a downsample if necessary. I think the stimuli are possibly saved in 128 hertz. The EEG is saved in 64 hertz, so that's what this is doing. Then we're going to extract some of the stimulus features of interest. So as Giovanni said, we're keeping all of these in C&D format, which means that we're going to have our main structure here with some fields. So I'm going to look at the stem E. And these are going to have names, some indices for like what stimulus. And so this is a very simple experiment. The indices are going to be the actual number of the index because they were presented in order. But you might have an experiment where participants had something in different order, and that's where those would go. Same thing here. If you have different conditions, you would put it there. We're not going to use these because these are all in order. And then you have data, which is a cell array that is a 1 by number of trials. And within that, it's going to be time by features. So if I just plot this one thing. Oh, it's off screen. That is so dumb. Why is it doing that? But you can see the envelope here. I'm just going to get rid of that because I don't like that. Of course, other features are going to have different amount of columns. This one has 19 columns because we're looking at 19 phonetic features, so on and so forth. And then we're going to have the EEG data that's organized very similarly. It has a similar order variable that you can use if you had to present in different orders. And then data is again a 1 by number of trials cell array. Oh, great. Mac is command plus slash and command plus T for comment and uncomment. Nice, thanks. And in those data, you have time by channels. We also want to make sure that all of the stimuli and the EEG are the same duration. That's specifically, well, not specifically, but that's important for the natural speech data set because the way that the data were epochs, it goes from the start of each trial to the start of the next trial, and the stimuli stopped a little bit before that. So you have to stop, or you have to make sure that they're all the same size. We also normalize the stimuli and the EEG. So we usually will take the z-score of the EEG, a z-score of any continuous stimulus, or if you're using an envelope, I tend to like to divide by the standard deviation, so none of the envelope falls below 0, but it actually doesn't really matter. So like the z-score and center. Oh. So apparently there were none of the pre-processed, there's a question, I'm unable to find pre-data sub 10, only data sub 10. So apparently there's no pre-processed data in there. You should be able to change everything to say data sub 10. So line 107, you can just delete pre and it'll work just the same. You might have some like worse results because it's not pre-processed. I'm sorry, I thought that there were the pre-processed data in there. So moving on, let me know if you have any problems changing that or if that creates any headache for anyone.
Or
Again,
Aaron,
yeah.
do you want to show them how to run the pre-processing code for one subject, for example?
Yeah, sure, I could do that. Actually, let me make sure that that's in. I'm going to send this, make sure this is being sent to everyone. Is it possible to send a link or send a file? Maybe not. I'm not sure if this script is in there, but you can, if it is, you can just specify.
I don't
Sorry,
see
Joe?
it. I don't see it in the email. I just see the CNSP tutorial and CNSP MTRF Toolbox
Whoops.
tutorial.
All right.
Or
Well, give me a
connect-
second. We've got 2 hours here. I'll send this out right quick.
Yeah, he'll share it in a
Hey, can
second.
you hear me?
Yep.
So I actually downloaded this stuff and ran the pre-processing and like created the files from the CNSP example 1. So basically one of the first sections of that file
Yeah, actually, I forgot
run
that.
the pre-processing with no bugs. Yeah.
Yeah,
Hope you
so
can
you
hear
can
me.
actually just open this file right here, like example 1 for TRF, or maybe any of these examples, but I just use example 1, and that's actually where I made the pre-processing script. Apologies, everyone. I'm sorry. I thought that I attached that to the email. What I would do is just for sub equals 10, and then you probably want to go down here and set a breakpoint so that it clear. You can see what's going on here. Why is it doing 18? Oh, I know what's going on.
Yeah, because the subjects are loaded in alphabetical order and
Yeah.
numbers are treated as not as digits.
Yep. So you might need to just run all of the subjects. Maya, how long did it take you to do that?
I don't know, maybe 10 minutes, something like that.
Cool. So if it's important for you all, then like you can run that file. I would just put a breakpoint at line 147 so that you don't go through and analyze the MTRF for all of the subjects. This should import the data sub file and save it back into the same folder. I will, as soon as I figure out how to reply all to all the blind carbon copies in the email. I'll send out the CND pre-processing script, but I'll continue on with the tutorial for now. Thanks for that, Maya, by the way. So just running the dependencies again and the parameters again, loading subject 10. Again, you can delete this for now, or you can run the pre-processing script on your own. So now we have our subject data loaded. So from here, after you get this section, loading and preparing EEG and stimulus features, any subsequent section can be run independently of any other section. But I'm going to go in order because it makes sense. So the first thing that we do is we want to fit a TRF. And so we do that by taking some stimulus feature, STEM-E, which is the envelope, and the corresponding EEG, and jam that through MTRF train. Here I'm selecting a random trial. You're going to get a different random trial. It's also going to look a little different because you're not using pre-processed data, possibly. But so what I'm going to do is I'm going to highlight and press F9 on PC. I don't know what this is on Mac. You can also just do the Control Enter or whatever the equivalent Mac function is, just to execute sections. Actually, I'm just going to do that here, just to get both of these. Damn it. Why is it? Oh, I know what's going on. It's my display settings. I'm going to have to lower my screen layout again. So apologies if people can't see the text so small. There we go. All right, so here we go. These are the two things that popped up. This is a single trial TRF. This is a multi-trial TRF, averaged across trials. We can see the single trial TRF change if we execute this code. Not that, I have to highlight all of it. Notice that it changes. I'm just going to execute it a couple times. You see that there's some consistencies there, and that's really good. I think the subject is a little, maybe too good to illustrate some of the things that we're talking about today. But each trial has some consistency to it. You see a little peak in the GFP around 150 milliseconds and one around 80 milliseconds. It's pretty consistent across time. That's great. That's what the TRF actually latches onto. So usually, so we can do that. So, and also you see that the multi-lag is just a better fit, lower noise across trials. But the whole point, or one of the whole points here, is to predict EEG from this model. So we could take this model and then use MTRF predict to predict the EEG. And I'm going to run it like this. And that's how long it takes to run. The output of predict and the output of MTRF crossval will be the statistic structure that's got two model fit metrics in it, the Pearson correlation between the predicted signal and the actual signal on that trial. Here we've got 20 trials by 128 channels. And it's going to be like that because there are no lambdas involved here. Sometimes in a crossval, you'll have a lambda dimension. So let's look at that correlation. .5, pretty small. That's about normal for an MTRF. But the problem with doing what we just did is that since this is an average model across all trials, and we're going to use that to predict each trial, it's using some of its own data to predict itself. So we're going to get a little bit of overfitting to that. And so the way that we combat overfitting a little bit here is that we'll take some of the trials. MTRF will do N-1 trial. We'll fit a model on those trials, and then we will take the fully fit model from those 19 trials and predict the left out trial with it. So to illustrate that, I'm going to change some of our hyperparameters. I'm removing the pre-stimulus and some of the post-stimulus time here, because when we do prediction, we really want to focus on the lags that are predictable. And by that, I mean the lags that have lots of components to it. So here I might say that it's 0 to 300 just by looking at this TRF, but I chose 400 at the, when I started this tutorial. So we're just gonna press on with that. This actually just makes it easier to predict. It's not trying to predict what is probably noise out in front of the stimulus and what is probably a little bit less signal out after the stimulus. And then we can run an MTRF cross-val. It takes a little bit longer to run than train and predict. But what this does is it's going to cross-validate or optimize a model and tell us which lambda produces the best predictions for those data. So here, we've got our best lambda, which is lambda 4. Just a little bit of something about the lambdas here. So this is our range of lambda. The higher the lambda, the more regularization, or the more emphasis that's placed on the diagonal of the XTX matrix. Usually the lambdas that work really well are in this range, and that's what we found here. It's 10. It's a little low for what I'm used to. I'm used to seeing 100 or 1,000, but whatever is whatever for each subject, and that's kind of the point of lambda optimization. We want to look at the correlation coefficient of that, or the prediction accuracy. We see that it's a little lower. That's probably because of some of the overfitting that occurs when we use the stimulus to predict itself. But we still do have a little bit of overfitting here because we're optimizing. We'll come back to that later. I'll fit a model with that best lambda and then visualize it. If you notice here, they're very similar. They're slightly different because they use different lambdas. That just means for this subject, this model does slightly better than this model, which is fine. That's what the point of optimization is. But as I said, there's still a little bit of overfitting going on in there. It's because of the optimization step. What actually happens is that, that's not what I wanted to see. I forgot to squeeze. Oh,
Aaron, we have a question in the chat. So from Camila, can you explain lambda a bit slower? Are you testing many lambdas for each subject, trial, model? What statistic do you use to select the best one? And yeah.
Yeah, so lambda, let me see if I can find a good picture. So here's an image of some XY data, weight and size, whatever that means. But we can imagine all of these dots relate to our data or are from the data, but we might want to like cross-validate our data. So we're going to use like a small subset of data, or maybe we don't have a lot of data. But anyway, so the fitting data in this is actually just the red dots, right? So we're going to fit a line to those red dots. And this line is just what linear regression would say is the best fit for that one. But the real best fit is actually blue. We don't know that though. What Lambda does, and why they would use ridge regression in this example, is that adding more Lambda will actually flatten out this red line until it matches the blue line, right? But you don't know which one's the best yet. So you fit a bunch of Lambda, or you can search for it or optimize it, but you fit a bunch of Lambda and then predict it on some left out data, so these green dots. And the Lambda that pops up or is the most optimal will be the one that matches the red line to something closer to the blue line. Does that make sense? Because we don't know it, we don't know where this red line is going to be. So we could have these two green dots be what we're fitting on. And so now the slope is too low. So we don't know which direction Lambda is going to go. It all depends on the fitting data. So that's why we would optimize Lambda individually. Let me see your question again. So
Aaron,
we do
just to
go for it.
add to that. Can you hear me?
Yep.
On fitting Lambda individually, or even say within one subject on individual conditions, just to kind of a note of caution, if you don't have very much data, so say you're working with maybe 5 to 10 minutes of data for a particular condition or subject, the Lambda that you will, I suppose, converge on, and the model that you will have as a result may not look very, how would you say, TRF like, or have components that resemble neurophysiological components. And the reason for that is because you don't have enough data, or your data are too noisy. And so I had someone email me recently where they were basically pointing out how for some conditions they had these beautiful looking TRFs, for others they were very noisy, a lot of kind of high frequency oscillating components, and that was most likely due to noise in their data. If you're trying to fit a model, if you're trying to fit Lambda just for the purposes of visualizing your TRFs to be able to make some sort of inference about the neurophysiology of your data, then oftentimes the best way to do that is, if you can't ensure that you have a lot of data, is to actually handpick a Lambda that enforces enough smoothing so that the resultant model weights begin to look TRF like. Otherwise, if you try to fit it using cross-validation, it'll probably just overfit to the data because you don't have enough. So, we use cross-validation for the purposes of predicting new data, whether you're talking about forward or backward models. But when you want to visualize the weights and do time frequency analysis on different components, you have to be careful about using cross-validation to do that if you don't have enough data. So we talk a little bit about that in the Frontiers paper, but that's just kind of a note of caution when you are fitting Lambda to your data.
Thanks, Beck. Just to add on to the add-on, the high frequency oscillating components that we usually see on the overfit data, that is explainable directly by this, I think. So when you don't have enough data, the fit tends to vary wildly. Like there's lots of excursions from the true mean. And so I think that's probably why it tends to not be smooth, is because the best fit to noisy data can be above or below, and it's sort of, you know, this line just goes back and forth. It's pretty unstable. This is actually taken from a really, really great video by a dude on YouTube whose channel is named StatsQuest, who has a really great example of ridge regression and actually like demonstrates how you can fit using one data point. I'm putting that into, oh wait, I'm putting that into the chat now. You also get a bonus song for each video. This guy writes these really dumb songs that are hilarious. So I highly recommend that channel. Really good explanations for complex statistical things. To finish answering your question, we do fit for each subject. It takes multiple trials to fit, so we include all trials at once, and usually we'll fit different lambdas, or like optimize lambda for different models. And like I showed, yeah, these are the two metrics that we use to select the best lambda. We have Pearson's correlation and then mean squared error. They both serve different functions. I tend to use the Pearson's correlation because it's invariant to scale, and whereas error is not. So error will enforce that the signal is at the same scale, and R won't. But what we usually do is to actually, I'm going to have to, I'll show you. I don't know what I'm doing. Anyway, what you should see is these 11 lambdas will each have like a different, oh, I know what I did. I've got best lambda in there. What a dumb mistake. There we go. So lambdas along the x-axis and the prediction correlation along the y. It looks like it's an asymptote, but it's actually not an asymptote. So if we zoom in here, it actually gets marginally better there. Not exactly sure if this constitutes the best lambda for this person, but it's sufficient. And this is kind of a common look for a tuning curve. Another, probably more common, is an actual tuning curve that's just like an inverted U. So we just usually choose the highest value there. There's some like issue with like maybe choosing like the knee point of it that might produce a bit better prediction accuracies, especially if you're like getting towards higher lambdas, but it's usually just the max of this middle dimension, whichever one is 11 here. All right. So I think that pretty much answers all of your question. So like I said, there's still a little bit of overfitting there because we're optimizing. If it's a good fit, it's not going to overfit very much, and that's what this will illustrate. So I'm just going to start executing here. So the optimal number of trials, I think Ola might talk about this tomorrow, but like we found that like 3 to 4 minutes of data is like where you start seeing an asymptote. So if you like data by like prediction accuracy, it starts to asymptote, and like this knee point's different for each individual, but it's usually like 4 to 5 minutes of data. So to get rid of this like optimization overfitting, what we do is we withhold some data from the cross-validation procedure. So here I'm putting all of the data into train, R train and S train, and then I'm removing the current trial. And then I'm making the test data that current trial. So I've got two sets here, one with 19 trials and one with 1 trial. Then we're going to do a cross-validation on 19 trials, find the best lambda, record that cross-validation prediction. Then we're going to fit a full model with all of those trials and the best lambda. And then we're going to use that model to predict that left out trial. And we're going to just run through all of the trials, rotating which one is the test trial. And then so it should have all of those test trials in both the cross-val and the left-out data. So that's what I'm plotting here. And we see this is a pretty well fit data set. There's enough data here. And maybe actually, this is back to where this might be too good of data. I tried a version of this where I only used like 3 or 4 minutes of data to fit, and I could just never get this to work. It only got better. So like the left out data is slightly better than the cross-validated, and that's probably just because there's very little, if any, overfitting that's going on in this step because there's so much data. So really, you only, like, this is probably more important whenever you are experiencing like noisy data, or if you have less data than, you know, what might be a well-fit model. So now we have a model. Now we have a cross-validated and a left-out like evaluation of that model, and it's performing at some level. We need to know how well it's performing, and one of the ways that we do that is to just determine its noise floor. If we have a fitting procedure that's not matching stimulus, or at least this is the way I think about it, there's other ways of thinking about it. If we have stimulus and response data that are not matching, how well can we, you know, fit a TRF to those data to predict left out data? So that's exactly what we're doing here. The first thing that I'm doing is to ensure all the trials are an even length, because they're not. Stimulus and response are matching, but across different trials, they were all different lengths because they were cut to be to end at a reasonable spot in the story, so it wasn't jarring for the participants. So each trial is a little bit different duration, and I'm fitting a different cross-validation on that. And then I'm going to run a whole lot of iterations. I'm not going to actually do this. I'm going to just preload this, which I've also sent to you. Here's a little trick for people in MATLAB. You type F0 and it won't execute that. But I'm going to run a whole lot of different iterations where I fit a model and then predict a left out model on its own data to see how well it can do. And then we're going to compare that distribution to what we actually observed on that model, or observed in the data. So I just really quickly ran 1,000 iterations of the MTRF. And that's what this is. This is 1,000 TRF models that have been evaluated on shuffled data. So we just shuffle the data labels. That's done like this, just with a rand perm. That's it. And then we compare that to what we observed. So like our observed is still, again, about 0.05. And the p-value on that are just tiny. So we can get the p-value by seeing how many of the null responses are bigger than the actual responses. If we look at the p-values, actually 1,000 iterations was not enough to get the actual p-value for some of these channels. There's one that was channel 50. Sorry, you are a loser. But once you have this model validation metric, you can use it to, you can like average across channels and see if those channels were better than a null model. You can do some cluster statistics on these. You can enter these into like an FDR correction, but here's your p-values. Just correct them however you feel the need. And that will tell you how good the model is. This model, of course, is very good. There's like no samples above that are from the null model. Of course, we might be interested in how different models compare. And those models can be from the same data, or they could be from different data. So we might be interested, what I'm showing here is like how well different speech features can predict EEG data. We might be interested in different trials predicting data, or we might be interested in different conditions or different people or something. But generally speaking, what we'll do is we can fit a model for each of those things that we're interested in. And so what I've done here is I fit a model to the envelope, fit a model to the spectrogram, fit a model to the phonetic features, and I've combined the phonetic features in the spectrogram model into a joint model so that we can look at how well these models compare. I'm basically trying to replicate Giovanni's 2015 current biology paper, which I actually did here. We see that the spectrogram performs better than the envelope. That makes a lot of sense because it's resolved better over frequency. It's the same data, but just more resolution. The phonetic feature model does perform a little bit better than spectrogram, but that's not really the comparison that we're after here. Like I mentioned earlier in the slides, what we're actually interested in whether the spectrogram and the phonetic feature model perform like uniquely, if they are like actually like finding unique parts of the EEG. And to do that, we can combine them and compare that to the constituent pieces. And that's what we see here. So when we add spectrogram and feature together, we see that it performs better than either model alone, implying that not everything that's in both of these is shared variance. There's some unique piece of variance in there. Of course, sometimes we need to take a little bit more care to make sure that we're not comparing models that are drastically different in terms of their numbers of parameters. And so one way that we can do that is to employ the permutation randomization approach again. Again, I have to make sure that the links are the same because we're going to do some shuffling. This takes a long time, so I didn't actually execute it. But so here I'm only going to do 50 iterations because we're not interested in the actual distribution from each subject. We're only interested in a single point for each subject, and we can compare groups of subjects together. But what we're going to do is we're going to fit another model that's similar to this one. It's going to have the same number of parameters in it, but only one of its features is going to be intact. And it's going to be the feature that we care about. And then this model is going to form like basically a baseline model, a null model that has all of the information in it that we don't care about. So for me here, that would be the spectrogram. So what we're trying to do here is we're trying to see how well the features encode EEG better than the spectrogram. So we have the spectrogram as part of this model, but we also have the phonetic features, but we're going to disrupt this phonetic feature somehow. Here I'm shuffling across the feature space. You can also shuffle across the trials. You can also shuffle by like reversing the feature in time. You can circularly shift, which means to take some part at the end and bring that to the beginning, and then make the beginning of that ending part the actual beginning of the stimulus. Just any way to disrupt the features. And so we will then compare the spectrogram model to the spectrogram plus feature model. So this spectrogram plus feature model obviously performs better than the spectrogram model, but when we add those extra nuisance regressors in there that are just shuffled feature model, it does get slightly worse. It's pretty marginal. Some people go up, some people go down, but generally this is about the same. So now we can compare these two if we really are like worried about like number of feature parameters, and this will be a more fair comparison with respect to that. So far we've gone in the forward direction, and I like going in the forward direction because I understand it a little bit better. I know what's going on. I can look at this and know this is the actual EEG response. It's physiologically interpretable. But one of the issues with going in the forward direction is that there's not much sensitivity. And so we can turn to a different direction to improve our sensitivity. And I'm going to change a few hyperparameters to do that. Again, I'm looking at a model, so I want to see a little bit.
There is a question from Maya.
Yeah.
Yep.
Hey, can you hear me?
Yep.
Yes.
Okay, thanks. So sorry, before just continue on to
No,
the
I
next
love
type
it.
of model. So
That's great.
Yeah, okay. I wanted to make sure I understand something about like the valuation of the different models.
About the what?
So if evaluation of the different models with the different predicting features.
Okay.
So like if I understand correctly, like line 387 of the code, so the combination of the spectrogram and phonetic feature model, so that's like an additive model in a way of these two features, modeling the EEG response. So
It's like this.
like with the but if like maybe in this combination of features it wouldn't really make any sense, but there are cases where you would like to look at an interaction of two features in modeling the EEG response. So like yeah, you can make a third type of feature that sort of combines the two, I guess. But like, would you have anything to say about that?
I've done that before. I don't know how feasible it is generally. The way I did it is I was recording EEG when people were watching visual speech. And then I had some stimulus features from the speaker. So one of the stimulus features we had were points on the mouth. So we track these 2 points and we track these 2 points. I'm gonna move where I can see your face, so I'm actually looking toward you. We track these 2 points and we track these 2 points. We took the distance between those, and we have these two like vectors for like how wide the mouth is at any given point and how tall the mouth is at any given point. And they were like yoked sample by sample. And we did 2 things. One is we fit a 2-feature model to the TRF, put the horizontal and the vertical in as separate features and predict it. And it does its own thing. And then another thing we did is we multiplied the 2 vectors and then did a 1-feature model. That's the best way that, so I did this in response to someone asking about mouth area and not mouth width and height, because a lot of things in the literature has to do with like mouth area. That was the best approximation that I could like get, was just to multiply those things. But like essentially when you're doing linear regression, you can just multiply your input features and get their interaction. I don't know if I would feel comfortable like saying that you're going to get a perfectly reasonable and an equivalent to like a linear regression interaction if you do that with the TRF. Mick might have like more thoughts on that, or Giovanni, or someone who's more expert in like the TRF than I am, but I've done that. Now, like with these models, you've got a spectrogram, which is a time series, but there's 16 of those time series, or however many frequency bands you have. And you also have a phonetic feature model that's a different type of stimulus. It's either a 1 or a 0. It's a 1 if it's on, if that phoneme is occurring or phonetic feature is occurring at that time point, or a 0 if it's not. So most of the features is zeros. So I'm not sure how you would do that practically with this type of model, where you have either a stick or an impulse or like a discrete model and a continuous model. Or if you have multivariate models, you're going to have to do like pairwise interactions, it seems. But I mean, other than that, there's no real way to do this with TRF. It's something that's interesting and something that I think that I would like to see the answer for. I'm not sure if, like, I can't envision like how you would want to do that or why you would want to do that, other than the question that I had from the reviewer. But I'd be very interested in like those cases and like what we can do with that. Yeah. If you have like thoughts on that and you want to email the CNSP Gmail with like some thoughts, I'd love to hear them. It might be something that we can add to the toolbox.
Cool, thanks very much. So actually your example really answers a lot of things, and sorry for taking a second more of time, but like in a way you could imagine that there would be like an effect for the like x-axis, y-axis, and an additional effect like for the like the interaction between them, right? So like would running a model with these 3 features be feasible, or you think not? Because
If you could-
describe a situation where just running the interaction and just the other two.
If I was truly looking for an interaction between two external like feature spaces on the output variable, I would probably run the features separately and with, sorry, let me rephrase that so I'm clear. I would run a 3-feature model, both main effects and the interaction term.
Yeah.
Yeah. But like running the interaction on like by itself can also make sense. I wasn't running an interaction. I mean, I was implicitly doing it. I wasn't intending to find an interaction. So like my mouth area, whatever it was not intended to be an interaction, but I mean, it essentially was.
Okay, great. Thanks very much for the time.
You're welcome. Yeah, and don't worry about wasting time. We're like 2/3 through here and there's still 45 minutes left. Lots of time to talk.
So I have a question before you go into the backward model. When you compute the forward model, so you try different lags as you show in the matrix.
Yep.
Do the lags have like physiological validity in a sense? Do they mean something about how the subject is processing the stimuli? Does that make sense? And is it saved for each subject somewhere, or you can actually use it as a, say, dependent variable?
Yep. So this is saved. So this is just how, let me go to the code for that. So when you fit a model, you just use TRF train. And then it spits out this variable, model. And that variable looks like this. It's got the weights. This one here, I believe, is for features. So if you're doing a forward spec, actually I could just, no, I don't have that yet. If you're doing a forward spectrogram, this should be 16. And then this is your bias term, which is your intercept term. We usually just ignore this, and it's just kind of, I don't know, we don't really do much of anything. The time variable, and then other stuff. So here's, the important part of the model, and that gets fit on whatever you input into it. So whatever this is and this is what that model represents. In this case, it's a single subject. This can be saved. And in fact, like if I was like, something like that, I could something like that and save all the models in a model structure. And then we have, what's called, in the libraries or somewhere, probably not there, is an MTRF model average that you can input something like that into, and it will average across subjects or across whatever iterations. I would fit for each subject. And then you can then take, this can be analyzed just as the same as an ERP. So in terms of like the GFP, we can like take the GFP here, or we can take the actual, like on specific channels, we can take the channel weights. We can find a peak here and see how far that is past 0. You can analyze these in any way that's like similar to the similar to an ERP. Something that I would be like caution against is to fit TRFs, or to optimize TRFs and then compare TRFs. So the TRF weights, if you notice, I've put here that it's in arbitrary, what did it do? Arbitrary units. That's because the lambda actually, it will like it will move the slope. So the more lambda you have there, the more the slopes moved, and the flatter things get, and the shorter, the less amplitude the TRF has. So if you compare like my TRF to your TRF, and my TRF has a higher regularization value, yours is going to be way bigger than mine. And mine's going to be way more spread out in time. So what I usually do if I want to compare TRFs is I apply one single regularization parameter to everyone. Just, I might optimize everyone, then take like the mode or a median or a mean or something like that. But I think it's pretty important to get like all of the TRFs in the same like amplitude space, and you do that by using the same lambda. Can you normalize the weights? What do you mean by normalize the weights? Do you mean like put them on a scale between 0 and 1? If that's the case, I mean, you could do that before you average them together, but
And you
then
normalize the weights, like in a, you take, yeah. So you maintain the topography for each subject and you normalize them, then you average them.
yeah, you can do that. But then you're getting rid of a lot of the amplitude information because the amplitudes always are the same. Normalizing before averaging, I'm not sure
Because
if
the
that,
amplitude within a subject should maintain, right? Like if you have like N1 type P1, like the components should be.
yeah.
I wouldn't advise normalizing before you average. I think you're better off normalizing the input data to your model, your EEG data, your stimulus features, and then whatever comes out the other end in terms of weights, average. I mean the scale on the x or y-axis for your weights, it doesn't really have much meaning. It's more so just to be able to look at the relative amplitude compared, across conditions or subjects. So personally, I'd advise against normalizing weights.
Yeah, I have a comment there. Sorry, I'm on the train now, so my microphone is terrible. I agree, Mick, in general, but there are some situations where you can have maybe have a little data, and you have some subjects that if you optimize the lambda on the single subjects, you can have some subjects that really explode. So there it might make sense to normalize. But if you are doing what Aaron was saying before, where you select one lambda for all the subjects, then it doesn't make much sense to normalize anymore.
Okay, thank you. Yeah, I was thinking of this, you optimize a model per subject, and then you have like a topography for each one for the weights.
Yep.
So you can normalize, you take the maximum value per subject, and you have this normalized TRF per electrode, and then you can average across subjects. Like that was my...
Yeah, but again, you're throwing out your amplitude data because everyone's going to be at the same scale.
It's relative. It would be relative. Yeah. So if you have two conditions, maybe you wouldn't mind.
Yeah, I just wouldn't do any statistics or any like inference on the TRF weights themselves at that point. But yeah, you could totally do that. And in fact, I've played around with like z-scoring TRF weights when doing like generic data, or sorry, generic models. That's where you would combine models from like n-1 subjects and then predict data from the left out subject with that generic model, which is useful in cases where you might have like 3 or 4 minutes of data from everyone. So like fitting an individual TRF, probably not feasible with 3 to 4 minutes, especially in the folks that you have to deal with 3 to 4 minutes of data. So like, people like babies. So you can utilize all of the data that's there from all the other subjects and then average that all together. And so like get more time, as it were, in your TRF by using other participant time. And then I think normalizing across subjects actually helps, especially if you have 1 or 2 subjects that drive the TRF, so you can get a better generic model. But yeah, like what we were talking about though is mostly for analyzing the TRFs themselves, which I would not recommend normalization. Cool. Again, feel free to interrupt me. I like interruptions. So like I said, this is in the forward direction. The ability to predict EEG is hard. EEG is noisy. And we're also using a one-dimensional stimulus, in this case, the envelope, to generate all of those predictions. In the reverse direction, we get to use all of the 128 responses to optimize a prediction of one thing, the envelope. And so we can really improve our signal to noise ratio. So we're going to change a few hyperparameters just to visualize the model. Do a control enter here. You see, first of all, that it takes a lot. Excuse me while I deal with this error. Oh, ha! Forgot about that. I got to fix all this stuff that I did. Where we at? Cool. So you can see it takes a lot longer to do a backwards model. And this is part of why we have that short set of lambda. So if this is taking a long time for you, then feel free to use that short set of lambda. You might want to change some of the lambdas to something higher. The lambdas that are in the short set are like -2 to 2. And backwards model tend to like high lambda. So you might want to change this from like 4 to 8 or like 6 to 10 or something like that. Anyway, you can see it was still running there. This is a good time for questions or whatever, if there are any. There we go. So here's your backwards model. You notice that it goes backwards because the way that it pops out, it's in stimulus time. So it's almost like a spike triggered averaging or like where you're averaging the EEG responses that occur as a result of or averaging the stimulus responses that occur as a result of the EEG. You see that they're like mostly mirror images in the sense that you've got these channels here. Notice that this red, purple, yellow, blue correspond to these channels here, red, purple, yellow, blue. Those are the same channels. But you notice something that happens close to the baseline is that over here in the forward model, we've got this nice looking like dipole where like the responses are sort of like separating in like potential space. But over here, because of the interactions of each across channels in the backwards model, where the backwards model is able to actually use some of these channels antagonistically to like sort of like increase the sensitivity. And when we compare what this model can do to this model, it's like not a question. So we've been looking at the average forward model prediction scores, which is a little bit misleading because the prediction scores have a topography. They are distributed across the scalp with the biggest one or the highest predictions usually right here, right over where auditory responses are in EEG. But we're just taking the average across the scalp, which also includes things around the back of the skull and the sides of the skull. So we're averaging a lot of like bad stuff in there. So if we look at the maximum prediction, that's just the channel that can do the best. And it still like doesn't even touch the backward model. So if you really want to like increase your sensitivity, that's what the backwards model is for. It takes a lot of time, so you have to be careful about, you know, running it on a machine that's, you know, doesn't have as much memory or has a slower processor. If you run into those issues, there is some. Am I running something? I am running something. Was it running? Oh, it's just that section. I'm going to cancel that. If you have like memory issues, there is an input that you can modify that will make it go slower, but it also requires less input. So the default requires more memory and is faster. And what that does is it pre-computes all the covariance matrices and stores them in memory, and it doesn't have to compute them when it's doing the leave one out cross validation. Otherwise, it does them while you're doing the leave one out cross validation. It's a bit slower. We also might be interested in when the response is most evident in brain activity. So, and I don't mean like the EEG fluctuation, but like which time lags are best able to predict the EEG. And so we, the MTRF toolbox can also fit what's called a single lag analysis by including this, on this, is it? No. By including these two inputs. And what this does is it will fit and evaluate the TRF at each time lag individually. That's not, so I'm running that. Give me a second to figure this one out. Oh, I know what's going on here. Just need the time series. Okay, use model 4 actually. Sorry about that. I guess this is what happens when you run this, not expecting to run it in the tutorial. So yeah, in 546, just change model to model 4. We already have those time points from this model that we fit there. I was trying to use this model, but since I didn't run, it's not there. And we can see the blue here is using the MTRF cross-val with the single lag. Something that I sometimes like to do, especially with some of our multi-sensory stuff, because we like to, we sometimes see a little bit of smearing in time, and we have sometimes see these little bumps that occur like before 0. And sometimes we want to be able to see if they are, you know, temporal smearing or something else. So what I also like to do is I have this little trick that I do with the MTRF toolbox, and that I will fit a regular multi-lag model, and then I will convert it to a single lag model by changing these two variables, and then predict on the individual lags. So sometimes this can like reduce some temporal smearing. You can see like a little, possibly a hump there that's maybe like fleshed out. This is not a great example, but it's, you know, it's there to illustrate that there's a little bit more temporal resolution if you fit all the lags at once. So the last thing I want to talk to you about is, didn't know if I would have time to get here. That's why it's at the end instead of up towards the beginning. We're going to go back to the forward direction. Is a way that we're developing. It's still not done. It needs to be done, but we're still like concerned about some of the issues with it. It's a way to actually remove the effect of some of the features before predicting other features. And by that, I mean like partialing features. So in the case of, I don't have it up yet there anymore. Do have it here. In the case of these, where we're looking at comparisons across different features, we looked at two different ways of doing that. One way is we can compare the joint model with each of its constituent models, or we can compare it with another baseline model in which we've shuffled a feature of interest. And then finally, one way that we can do is we can just remove that feature entirely from the EEG. So that's going to involve using the predictive power of the TRF by fitting a model, predicting its EEG, and then simply subtracting that prediction from the actual EEG. So this loop here will do that. And then we have all of this EEG, new EEG, that does not have the responses to the spectrogram. So I'm going to run this, see how long it takes. So here it's just fitting and training a model on each trial, removing the effects of that feature from the trial. And then we move on and we're going to optimize several models. One, we're going to try to optimize to the spectrogram when we have no spectrogram in the model. And then we're going to optimize to the phonetic features when we have no spectrogram in the model. And that's what this is looking at. So if we look at the FS model, it's the same FS model we've looked at. If we look at the F model, it's the same F model we've looked at, and same thing goes for the same S model that we've looked at. But then here we have an F and an S predictions that we have fit to EEG that has no spectrogram responses in it. And so here is a better look at the unique contributions of this phonetic feature model. I emphasize the word unique here because it's going to remove, or this process is going to remove most of the responses that can be correlated between either of the two. So this is going to have mostly F in it, but some of the F isn't going to be there. This is going to have mostly nothing in it. So this should have like no spectrogram, and then we fit spectrogram. This is just to illustrate that the process works. We're removing this much information from the EEG, yet we still have this much information left in the EEG that could be fit to the feature model, but not the spectrogram model. We also have been working with a different approach to this. Farheen Ahmed in our lab, who's just defended her PhD, and some others in the lab have come up with a different way of doing this. And that involves predicting all of the features that you care about, including the ones that you're trying to control for and the ones that you're trying to measure. And then using MATLABs or whatever functions, partial correlation to get the responses that are only correlated between these two while controlling for these two. So that involves, again, we're going to fit and predict on different trials. So we're going to fit a model to phonetic features, and then we're going to predict EEG to phonetic features. Fit a model to the spectrogram, then we're going to predict EEG related to the spectrogram. And then we're just going to go through all of the channels, and we're going to correlate the EEG data on that channel to the phonetic feature prediction on that channel. And then we're going to also account for the predictions of the spectrogram on that channel. And this is what that looks like. In this example, they're not equivalent because what I'm doing here is not optimal. In fact, most of these analyses and the tutorial script is not optimal because I've cheated a little bit. Not really cheated. I've made it go a little faster. I fit a single model up here with MTRF train to the stimulus envelope. I've done that here. And then optimized lambda for that one model. So just this is optimized for the envelope model, but I've used that best lambda all across the analysis. So there's a lot of suboptimality in here, but in an optimal environment, when we test this, these two numbers are almost identical. There's a little bit of rounding error and maybe some other minor differences, but generally speaking, these two numbers are pretty much the same. So there's two different methods for accounting for unique portions of the EEG, depending on what you're doing. This might be more easy if you need some spectrogram-free EEG to do some other TRF analysis, but if you really just want what is the unique contribution of S, this is probably faster. Cool. And so that's like the end of what I have prepared. And so I'll open it up to questions that go beyond this or questions that are related to this and what I covered. So everyone got to run all of that perfectly without the pre-processed data. Great.
Aaron, I have a quick question. The multi versus single lag analysis you were showing there, I think you still have it open, figure 10, where you were kind of doing a sanity check to see what the profile looks like when you use multiple lags. Are you like kind of taking an arbitrary window and just sliding it along, and then
No, it's the whole. It's all of the lags are fit at once. Let me pull up the code.
so how does as in like from minus 200 to 600?
Yep.
So how does the reconstruction accuracy then pertain to a particular lag?
Change it to a single lag model.
I'm confused now.
So when you fit a single lag model, did I save this? I don't think I did. I wonder how long this is going to take. Huh, that'd be fast. So, oh, that's not right. I should actually be doing this one. Oh, what is that? I don't like this new MATLAB. It's throwing up like stuff, and then when I like keep typing, it like messes up. I hate it. Might see if I can turn that off or go back to an old version. I don't know how long these are going to take. The T-max. Probably good enough. All right. So, oh, I just overwrote that too. That was dumb as hell. Model A and Model B. And do that instead. Oh, and also that's just one trial, so maybe that's why it's taken a long time. So Model A and Model B have like very similar structures in the structure. That was really silly sounding. Really, the only difference is that the single lags B has one for each channel, and then the multi lags B has one for each time point. And also the type is different. So actually, did I? Yeah. So I just made it compatible using the same like B variable, and yeah, it runs.
But what I'm wondering is the output you have, the reconstruction values.
Yeah.
How can you have more than one if you do a multi-lag analysis?
Well, I just fit a multi-lag model, and then I'm predicting the single lag model.
Right. Okay.
So when you do a multi-lag fit like this, it goes this time point, what is that? Fit it, predict it. This time point, what is that? Fit it, predict it. This time point, what is that? Fit it, predict it. And these aren't the weights, obviously, just telling that for everyone else on. These are the output, the reconstruction accuracy. What this does is it fits all of these models together, right? But when you do MTRF train with like type single, it'll fit this, and it'll fit that, and it'll fit that, and it'll fit all of these, right? And then it'll put them all together in the model structure, and then output that. And so that output model structure is like very nearly identical to the multi-lag model structure. I'm not sure if sorry, go ahead.
I was just going to say, it probably makes more sense to do it the way you're doing it with a multi-fit than a single fit, like in general.
Maybe it's a lot longer though.
The single fit stuff was always had the issue of not being able to account for autocorrelation in the signal.
Yeah.
And so this kind of gets around that, which
bit.
is why you always had that smeared profile in the single fit. So maybe you should go update the toolbox.
I mean, I think that like each one has their like utility, right? Like this one is super fast. And there's not that much. And it's something that, you know, we've been looking at a lot of like multi-sensory data, some of the stuff that Farheen's been like doing, and we're seeing a lot of stuff that occurs before zero. And the one paper that's in NeuroImage now, where she took your decoder models and used them in Ashling's eavesdropping paper, there's a lot of stuff that we chalked up to temporal smearing, and we put that in the discussion. I think this is like, maybe it's temporal smearing, maybe it's something else. We don't really know what it is, but then we kept getting some new like multi-sensory data, and it seems like there's actually some stuff that happens before zero, like long time before zero. And at least in the multi-sensory case, something that's occurring like out around here, it's probably the visual stimulus, because like, you know, Chandrasekhar and the visual stuff's like starting to move, you know, a couple hundred milliseconds before you hear it. So it's maybe that, but we're also seeing some stuff that's like 300 milliseconds before onset time. And like, that seems like it's not like within the realm of the temporal smearing. So yeah, I mean, it does help. How much does it help? I mean, you still have like these two components that are from each of the two peaks in the GFP. You still have this something late around 400 milliseconds that, you know, mirrors like what's going on at 400 milliseconds in the TRF. I don't really see that this is actually helping a lot in this particular situation. And I think that's because there's a lot of good data in this. There's like 20 minutes of, actually no, it's more like 60 minutes of data. Anyway, yeah, I'll stop belaboring the point. I do like my way, obviously, but I like the fastness of your way. Anything else? Just yell out. How about like if someone has like ideas, if they're wanting to do with the TRF, and you're trying to use the TRF to analyze your data, and you have some issues, maybe tell us what you're doing with your data, and any questions that you might have about that. It doesn't have to be about the tutorial. Now, this is a like tutorial about the TRF toolbox, but I mean, mostly it's just we're here to help you. And so if like the tutorial was enough, great. But while we're here, might as well grill us. I'm gonna stop sharing so that we're all on the call.
I'll ask a question.
Go for it.
So
and the rest of the organizers, please feel free to answer here too. It's not my show. Sorry, go ahead.
Yeah, so I have data on speech processing in children, and it's longitudinal data. So I really want to use that data because it took a lot of effort to take, but I had technical issues. So I had a lag between the stimulus and the response, which I don't know. Well, it's variable and I don't know how long it is.
The variable is the issue.
Yeah, I know. So I was wondering whether, given that you're like shifting the stimulus and the response, like could you just shift it until you find the best lag possible and then just use that?
Yeah, actually,
overcome that technical deficit.
Yeah, it can. I think you got to be a little careful there, I guess. But I mean, you can. The TRF doesn't really care about that lag. Actually, it's just going to find whatever lag corresponds to like some relationship between, oh, this happened in the EEG and this happened in the stimulus, and that is like really consistent across trials. So that's really all it cares about. The only issue would be, from my point of view, is if there is a variable lag across trials. it might take some cleverness and also maybe some like human like hand holding of the TRF function. So like, for example, you don't want to just do an MTRF cross-val if the time lag is variable across trials, because what will happen is you'll get a TRF of the component here, a TRF of the component there. We'll average them together. We'll get a smaller TRF that's like kind of has 2 humps in it, and we're going to try to predict some other data where that hump should be variably somewhere else. What I would imagine doing is running a bunch of MTRF trains on some different trials. Maybe doing a cross-validation between, a cross-correlation between the MTRF weights between each trials. You might have like one standard trial, and then you say, this trial, what's the maximum cross correlation? This trial, what's the maximum cross correlation? And you can use the lags from the cross correlation to maybe align the TRFs. And then once you have them aligned, you might be able to use that alignment to then go back and do an MTRF cross-val after you adjust your EEG like stimulus like alignment. Does that make sense?
Makes sense. Sort of. I would have to try it, but yes.
But like if I were to take stimulus and EEG and they're time aligned perfectly, and I MTRF train it, and then I take the same stimulus, same EEG, and I like add a lag, MTRF train it, and I go back and add another lag, MTRF train it, and I record these lags, I can apply that lag to the TRF, and then they should, Mick, Joe, Steph, someone, correct me if I'm wrong, they should align perfectly. Given that you have the same regularization parameter, it's the same trial, all the same signals, it should align perfectly. That's a really cool, I'm really sorry about that like situation that's like an EEG person's worst nightmare.
I know.
But it's a pretty cool situation, from my perspective, because I don't have to deal with it in a way that like the TRF might be able to help you. And it just like, I don't know, I think that it'll be fine. I think that you can like fix that with something. And I don't even think it's going to need to be a TRF. Like the TRF here is just a stand-in for something that is invariant to time lag. You could use other things. So we've got a guy in the lab, Jin Do, who is looking at semantic responses. So the N400 response. And of course, I'm just waffling now. So like if anyone has an actual real question, please ask it. If you just like to listen to me talk, great. So Jin has, he's looking at semantic responses, which we usually index by the N400. So what happens in N400, if you're not familiar with it, if I tell you the dentist told me to brush you have a prediction, and then I say free, and that prediction is violated. And that violation of the prediction is evident in a larger negative component 400 milliseconds after I said tree. So we studied the N400, but we always had a question of whether the N400 was optimally fit by a stick model at the beginning of the trial, or at the beginning of the word, because you're listening to a word. If it's a short word, you're going to get the meaning of it almost immediately. If it's a long word, you might have to sit there and listen to a few phonemes, and it's not enough time to like really affect behavior and like conversation. Maybe it is if you're, have a hard time if you're speaking a site, whatever. But those, 100 milliseconds that it takes you to understand the word might not be a big deal behaviorally, but neurally, that's a long time. So Jin has developed a neural network that can fit semantic TRFs by varying the timing of the impulse that corresponds to each word, and he gets better predictions. They're marginally better because the semantic like prediction accuracies aren't that high anyway, but we do get significant cross-validated improvements by like varying the stick. All of that just to say that you might be able to talk to someone who can fit a TRF using a neural network where time is a parameter.
I have a few
Thanks.
questions.
Oh, okay,
Two different questions.
cool.
The first one, in our projects, well, our previous projects, we usually have two stimuli that are playing concurrently. And we usually do different analysis to see like in selective attention, divided attention, paradigms like that. And we've always debated if to enter the two stimuli envelopes into a multivariate model, or if we want to compare the responses between them, if to put them into the same model, or if to put them in two different models. And we were wondering how, because of the issue of cross-validation, if we were, for example, comparing attended versus unattended, if we put them in the multivariate, if that will affect, if one's responses are lower, if that will affect the total performance of the model, if the difference between them is big.
I don't think so. I ran an experiment where I had noise, and then I randomly changed its envelope, and then there was a visual flash on the screen, and its brightness was changed by a different envelope, and I can TRF them separately and together, and when I TRF them together, the performance improves because you're accounting for more data, right? There are some responses in the brain that are responding to your unattended stimulus and some that are responding to your attended stimulus. And if you input both into a multivariate TRF, you should be able to do better. Their weights might be affected by the multivariate approach, but I would guess probably not much, since they're probably not correlated. Probably the biggest interaction there is actually what's going on in the brain, rather than what's going on in the modeling procedure. You've got like neurons that are unable to respond to one because they're you're attended to the other one. Am I getting close to your question? I'm not sure if I quite understand your question. You're worried about whether the modeling procedure will, or whether entering them together will affect, make a worse model? If
for example, in our experiment, one of the stimuli was a very rhythmic stimuli, and we found that when we put them in two separate models, the model was there was no speech tracking at all for the rhythmic stimuli, and we wanted that's a whole different question that we wanted to look into. But then we were wondering if when we put them together, when we looked at the model, the multivariate model, it seemed to look worse than when we would just look at the the continuous speech or the other stimuli by itself. And we were wondering if there was something maybe that we should done maybe to control, or to do something in between, so that we could enter them into the same model instead of looking at them in two separate models.
So let me just summarize what I think that you did. You have speech A and B. You fit a model to A. You got a TRF for A. Not the reconstruction or not the prediction accuracies, but the TRF itself. Yeah. Fit a model to B, you get a TRF for B. You fit a TRF for A and B together. And then you're going to take the A-B model, separate it into model A, model B, right? And you're looking at model A from the joint model, and model A fits similarly side by side. Yeah. And the same thing for B. Both of those look worse when you...
the B was bad either way, but okay. The A looked worse in the multivariate model.
A is the rhythmic speech?
The continuous speech. No, A is the regular continuous speech, and B is the
very rhythmic,
onset of words or come at a very specific rate.
feel like
Um,
something is going on here that's not, well, maybe not, I don't know. Are you using the actual envelope for the rhythmic speech?
Both of them, yeah. Both of them. is open.
Are what is being spoken words?
Yeah, yeah. I mean,
Okay.
words in like in phrases.
Okay.
Like it's just the onset of the words is just regular, like regularized.
Well, what I was going to say, which I'm less concerned about now, is that the TRF does not like rhythmic things. And as Ed would say, it would shit itself. But that applies more to things like sinusoids and things that are like regularly rhythmic. And I don't think that's a TRF issue. I think that's just a linear time invariant system issue, which I say those words, I don't know really anything about them. So if you want to hear more of those words, ask Nick, probably. Giovanni, I don't know. But yeah, I'm not sure that's actually the problem.
And then I have another question, sort of about
Let me follow up on that though. Email us that,
something
and
that you
I
spoke
kind of
about
want to have a
earlier.
think about that a little bit more. Okay.
Okay.
But go
Yeah.
ahead with your other question.
So another thing that we're doing now is also we're looking at this like one stimuli, the envelope, but we're also adding the other parameters, so other features such as word onset, phoneme onset, things like that. And we were just wondering, and you might have spoke about it today, but I was trying to like run the code, so I wasn't always with you. But
I know how it be.
but how would you specify exactly, if I want to understand if adding these features improved my model, what baseline or what criteria should I set so that I can understand whether adding each of these features actually made my model substantially better? Like, how do I know between these R values if this is better than just looking at the envelope?
We usually just do like a paired samples test between the two, like
Would you
prediction
do like
accuracies or
separate models? Would you do like
Yeah.
separate models for just the envelope and then like with each feature and then compare?
Yeah, so here's the thing. If you put features together in one model, you're only going to get one output.
Right.
So each interior, I'm gonna do this again. All right, do we have MATLAB?
Yes, we see it.
Yeah. So here's kind of, hold on just a second. I'm gonna actually show some data and we see a paper. So this is from your man, Giovanni, just left the call, had to get home. So this is what he did. That envelope spectrogram, phonemes, phonetic features, and a joint model with phonetic feature and spectrogram. He pretty much canned phonemes from the outset because phonetic features is a smaller model, it does better, and it does better generally. So this is what he does. So this is an MTRF cross-val. That's an MTRF cross-val. That each one of these is a different MTRF cross-val for different people. So however many people he has in here times 5 is the number of models or cross-validations he did for this. And that's what this is right here. So one thing I actually didn't mention is that like I'm only going to do an MTRF cross-val for most of this. I should have mentioned this at the very beginning. That's my cat, by the way. This is really the way to go, unless you're pretty sure that you're not overfitting, is to have like a separate train and test set. So even though like it would be one of these for each of those 5 conditions, but here I'm just doing that for each condition. So we get a value here, a value there, and a value there. or actually we get 128 values. You can do different things, but I'm just taking the average across the entire scalp. But
And you wouldn't do combinations?
you
You would
would.
just do them all on their own?
You have to do both. Oh, forgot I took the damn. That's my own function, and I cleared my own variable space, so I'm not able to show you the topo plots, but they do have like topographies. Actually, no, I do have this to show you. So they do have topographies. And so like this is like not very good. This is or not very optimal. So you can like choose whichever like channels you want. Like something like that. If you've defined some channels, and that will improve it. But you have to do, this one is an envelope, one feature, spectrogram, one feature, phonemes, one feature, or phonetic features, one feature. This is a phonetic feature spectrogram, and it was made with two features.
Got it.
I will actually just show you this, just to illustrate what it looks like. So this is time, 11,365 by 1. That's the envelope model. The phoneme or phonetic feature model, I keep calling them phonemes. 1,000 or 11,365 time points by 19 features. I call this one feature model. It has 19 parameters in it, 19 features. So it gets entered in as 19 coefficients, but we treat this as like one set of features. The same thing with the spectrogram, 16 channels of 16 frequency channels, and the FS is now 35.
How does
So
it
that is,
know, like, just from, this is like maybe a code question, but how does it know in this case to treat all of what's, because this looks exactly like how I would enter the, like when I enter my my stimuli and I want to enter the different features, I enter them, like I enter time times 4, which is like the 4 features. So how does it know in this case
it
that
doesn't,
to treat them as one?
it doesn't. It will always treat each of these as separate, but it will add them together at the end. Ish. So at the end, we're going to add 16 features together for the spectrogram model. At the end, we're going to add 19 features together to get the ultimate prediction in the feature model, the phonetic feature model. And then we're going to add both of those features together at the end. So you're going to have like essentially, and I'm kind of like bending the truth a little bit here. You're going to have like 16 spectrogram predictions and 19 phonetic feature predictions. And so the spectrogram predictions are only going to be those 16. The phonetic features are only going to be those 19. And the combined joint model is going to be all 35. So that's how you get the, yeah. But it's not smart actually, in terms of like treating columns differently, and it doesn't really need to be. We do have, we have worked on something called banded ridge regression. And that's where we do treat bands of features separately. As we don't have this yet, and I've got it written, and I'm just not happy with it, so we aren't releasing it yet. But what it does is it treats bands of like features, like say these 16 spectrograms, bands, or 19 phonetic features as one set and regularizes them all together the same, but potentially different from the other features. And so like, and that's useful because the amount of regularization depends on a lot of things. So like things that are not like pertinent here, like the data quality, how much data you have, and stuff like that. But pertinent to this, another thing that matters is like the type of feature. So like if you've got a sparse model where you've just got a bunch of zeros, and then somewhere in there, there's like ones, and most of your data are zeros. Or if you have a feature that is substantially different temporal dynamics. So for example, one of our old grad students, Adam Bedner, did an experiment where he had someone listening to speech that moves in space. So someone's talking and it's just sitting here moving like this across space. And their goal is to track that in space, right? Well, it moves way slower than it's speaking. So I'm like speaking in normal speed and I'm moving my hand about how fast it would move in space. So this like feature, like compared to like the envelopes, it's really slow. And so if I were going to fit a model with that envelope of the motion and an envelope of the speech energy, I might want to like regularize them differently because they have different frequency characteristics. So that's one way that we can use the TRF to like treat things differently, but that doesn't really do anything other than change the regularization, but that provides the optimal lambda. If you fit a spectrogram model and if you fit a phonetic feature model, you'll see most of the time the phonetic feature model requires a higher lambda probably because of like this sparseness. But otherwise, you don't really need things to be treated differently because it's one model, one prediction. How well can it do?
Thank you so much.
You're welcome. And 17 troopers here, just wanting to like hear just all of my waffle.
Okay, thanks everyone very much. I'll also believe it's 10 p.m. Jerusalem time. So.
Yeah, so like that's all I have, and I'm only here if like you need extra help.
Thanks.
Yeah. Okay. I'll give someone like another couple of minutes to speak up if you're shy, but after that, like we'll call it a day.